Right, let me start. So hello everyone. Welcome to RSMA Webinar Series 2025, organized by IEEE Communication Society, WTC Special Interest Group on RSMA. So my name is Wonjae Shin, Associate Professor at Korea University, South Korea. So this is our fourth webinar series this year. It's our great honor today to have Professor Jinseok Choi from KAIST, South Korea, as our distinguished speaker. So please allow me to make a brief introduction of Professor Choi. So Professor Choi is an associate professor at Korea Advanced Institute of Science and Technology, and he received a bachelor degree at Yonsei University and a master and PhD degree at UT Austin. And prior to joining KAIST, he served as a senior system engineer in the Qualcomm San Diego and assistant professor at UNIST, South Korea. So he currently holds adjunct professorship at KAIST Institute for Security Convergence and G School and LG KAIST 6G Center in recognition of his contributions to energy efficient communication. He received several awards, including IEEE ComSoc AP Young Research Award in 2023. So he served as an associate editor for TWC and OJ Comms. So his research focused on developing and analyzing future wireless communication system, including energy efficient communication and new multiple access technique in IoT communications and satellite communications. So before the talk, I'd like to remind the rules of our webinar. So during the 50-minute talk, please keep muted and you can type any question if you have in the chat box. So after the talk, we have about a 10-minute Q&A session. So please, you can unmute it yourself and to raise your question. Otherwise, I can pick up several questions from the chat box. So, all right, so enjoy the talk. So let me stop sharing the screen and Professor Choi, the floor is yours. You can share your screen and start your presentation if you're ready.
Okay, thank you for a nice introducing me. So can you all see my presentation slide in a full view?
Yeah, perfect, yes.
All right. So, okay, so firstly, let me introduce myself. As introduced, my name is Jinseok Choi. I'm currently an associate professor at KAIST in South Korea. So in today's webinar, I'd like to introduce some of the key pre-coding technologies related to the RSMA, and then how it works well in the power, show how well it works well in the power limited systems for the free 6G. Okay, so these are the contents of my presentations. I'll first review the 6G trend and challenges, and I'll give you some key system solutions related to the challenge and introduce two different types of optimizations for the RSMA pre-coding, and I'll conclude my seminar. So the 6G trend and challenges. So 6G communication, as you all know, requires very stringent requirements in terms of very many different directions, such as data rate, energy efficiency, spectral efficiency, and so on. So all these strict requirements compared to the 5G can be enabled by tackling those different directions. By increasing the bandwidth, we can increase the data rate. And by increasing the number of antennas, we can increase the efficiency. And also, hardware can be low power hardware can be used to reduce the power consumption for better energy efficiency. And we can also change the multiple accessing techniques such as the RSMA or the NOMA. And the frame structures can be accordingly changed to keep with air latency and some reliability aspects. And networks can be changed, like the UAV network can be introduced, or LEO satellite network can be introduced to extend the coverage, and cell-free as well. But then I'd like to talk about the key link trend among all these. So the antenna massification and the bandwidth massification are the key link trend in wireless communications. So antenna is going to be massive. So as you know, all this term, this massive MIMO has been introduced and actively investigated in both in academia and also industry. Because by introducing the beamforming, we can have better directionality of the beams, and which obtains better channel gain for the desired user and reducing the interference to the undesired users. So this has brings very significant improvement in DSNR, and we can also use this for like multiplexing technique. So it can give you the rate increasement. And also the bandwidth specification, meaning we're going to use wider and wider band by increasing the frequency. So if we use a bandwidth like 10 times wider than the current bandwidth, then theoretically we can increase the data rate by like 10 times. So it's going to be a linear increasement in the data rate with the bandwidth. And what's better with the high frequency is that if we use, for example, millimeter wave antenna, these are like 128 antennas packed in a very small area for the millimeter wave. So we can reduce the amount of the area size for compactly include all the massive antennas. So it's going to be very handy. So all these directions are like the future mobile wireless communication directions. But unfortunately, as you know, the millimeter wave does not achieve that much success in the 5G. So 6G is targeting the upper mid band, which ranges from 7 to 24 gigahertz. And we are expecting to utilize around like 400 megahertz of the bandwidth, but it's still wider than the current bandwidth. So increasing the bandwidth and increasing the antenna size, antenna elements, maybe you can achieve a better rate, dramatically increased from the current data rate. And then in terms of the network trend, we can also say that the network becomes more massive. So traditionally, we have like base stations deployed with most of the functionality included in each base station. However, as the network trend evolves, we have more centralized functions for the common functionality of the base stations. So the base station, which is called like our remote radio head, has a lighter and lighter functionality with themselves. And then now we have like virtualized RAN and open RAN, and this centralization becomes more and more significant. So the most of the functions are retained in the central unit, and we have very light RRUs. And then these RRUs, number of RRUs is expected to be larger and larger in the future. So that means that not only the antennas, but also the number of RRUs will increase in the future. Then what happens? So these all give you a better like rate and better coverage, and in all, it's better in most of the wireless communication aspects. However, increasing such like antenna bandwidth and number of RRUs eventually increase the power consumption. So for example, the ADC power consumption linearly increases with the bandwidth. So if we increase the bandwidth, we have the linear increase in the power consumption. And then increasing the antennas also increase the number of ADCs. Increasing RRUs also increase the number of ADCs in the network. So we cannot avoid like massive power increase by when we increase the antennas bandwidth and RRUs and etc. So I guess this power consumption can be the big issue, which prevents our like 6G implementation from the realizations. So I recognize reducing the antenna ADC bits as a key system solution, and I found that RSMA can actually work very well with lowering the ADC system. Now let me tell you why. So here, if we reduce the number of ADC bits, we are going to have very like quantized system, and which introduces the non-recognizable quantization error. So these errors increases with the signal input, the quantization signal input, as well as reducing the number of bits. So reducing the number of bits dramatically reduce the power consumption of ADC. Meanwhile, it also increased the quantization error significantly. So as you see the figure on the right side here, it is a spectral efficiency versus the SNR. And then this spectral efficiency increases as the SNR increases for the perfect quantization case. When SNR is low, if we reduce the quantization bits, the degradation from the quantization error is very small. However, if the SNR increases, since the quantization error becomes larger and larger with the signal power, we have more degradation from decreasing the number of bits. So at the end, it saturates to some point. So we have to carefully investigate how to optimize this quantized system. And the rationale behind this behavior is here. So for low quantization case, where y is equal to x plus n, the signal to noise ratio is given by this. And if we increase the transmit signal power to the infinity, this SNR goes to infinity. So we can keep increasing the spectral efficiency theoretically. But if we have the quantization effect, we have some quantization. So in a kind of linear approximation form, we have quantization loss and the quantization error. So because of this quantization error increases with the signal power, the SQNR will converges to some point with infinite transmit power. So it cannot go to infinity, and it converges to some small value, as we can see from this figure. So the challenges in reducing the quantization, reducing the number of bits, give you the quantization error, and then subsequently, as a side effect, reduced quality of the signal can result in the channel estimation error accuracy. So all these can contribute to increasing the interference as well. So I recognize that the RSMA can be a good solution for this low resolution ADCs where the interference is likely to be higher than before. And then there are several multiple access techniques to mitigate the interference, and the RSMA is the new and the best one, I guess. So SDMA was proposed in the very early MIMO systems, and 4G is targeting this SDMA as a key multiple access technique. So this spatial division multiple access basically use spatial degree of freedom to nullify interference. So by nullifying the interference between the users in a spatial domain, the users will have very small interference. And then maybe we have the remaining interference can be treated as noise when decoding. So it's very easy to perform. However, it's kind of hard to handle the high interference when this degree of freedom is limited or channel estimation error is large. So NOMA has been introduced as a key multiple access technique jointly used with SDMA. So NOMA is basically non-orthogonal multiple access technique. It superposes the signals in the same degree of freedom, and then the users with the strong channel will decode the weak user's symbol first and then cancel it. So the strong user can decode its own signal without any interference. However, weak user will decode W2 its own signal with the interference from the strong user. So it's very powerful interference decoding solution which achieves the capacity. However, it's very sensitive to the decoding order. So we have to find out who's the stronger user and who's the weak user to identify and to maximize the potential of the NOMA. If we have a single antenna and a few users, maybe it's very easy to find out the order. However, think about the MIMO pre-coding case with the multiple users, then the stronger user will change if we change the beamforming. So it's like a chicken and egg problem, and the decoding order is going to be very complicated. So in 6G, RSMA, the rate splitting multiple access, has been introduced and widely actively studied. So it basically split the user's signal messages basically split into two different parts. So a private message and the common message. So here also private message and the common message. And then these common messages are combined together to generate one single common message. So these three messages, like private message 1, common message, and private message 2, are transmitted. And at all users, they decode this common message first, and then cancel it, and they decode their private messages. So basically, it's relatively easy to perform because we don't need to know the order here, just like the NOMA. And it's also good to handle the interference because by canceling the common message, the private message experience less interference. So RSMA is a very powerful solution. And then theoretically, it's been proved that RSMA basically achieves the optimal DOF compared to the orthogonal multiple access or treat interference as noise method or the interference decoding method over any interference regime, so weak or strong. Regardless of how weak and how strong, it's very adaptable and it's robust to all these regimes, so it achieved optimal DOF. So RSMA basically bridges the SDMA and the NOMA, and it can be used for this downlink broadcast channel. So we have the multi-antenna at the base station, then the single common message can be pre-coded with the common precoder, and the private messages or private streams can be pre-coded with its own precoder. And then I'm going to introduce this low resolution DACs at the base station and see how well this RSMA can work along with these quantization errors and this all power limited behavior. So in order to introduce provide the evaluation of the RSMA in the quantized pre-coding optimization, I'm going to first introduce the rate-only RSMA quantized pre-coding optimization, meaning we are going to optimize the spectral efficiency, basically. And in this model, I consider the downlink multi-user MIMO model. So we have the multiple antennas at the transmitter or the base station, and then we have K users, and K users messages are splitted into common message and its own private message. And these common messages are combined to generate the one single common message. The encoder will generate this common stream with the private streams. And then those streams are pre-coded and then quantized at the DACs. So these DACs will introduce quantization error, and then this signal will be transmitted over the channel. So for this downlink multi-user MIMO case, the summary maximization problem is given as follows. So RC represents the common rate and RK represents the private rate. So we have to maximize the sum rate by optimizing the precoders subject to the transmit power. So in typically in perfect quantization system, the common rate is the minimum rate of all common rates for each user, because all users have to should be able to decode the common message. So it should be the minimum of the all common rates. So this minimum function introduces like node smoothness. Later, it will be challenging to solve the optimization problem with the minimum function. For the private messages, it's just a regular SN log 2 1 plus SNR, but noticeably we have inter-user interference, and this inter-user interference doesn't have the common message in it because we assumed it's been canceled after decoding the common message at each user. However, when it comes to the imperfect quantization, we have common message and the private rate, but we still have the quantization errors in it. So we have careful optimization is required to handle quantization as well as the inter-user interference. So let me first focus on the quantization effect rather than the channel estimation error. So let's assume the perfect CSIT and solve this problem. And I can categorize three different challenges, such as node-smooth function in the common rate, and quantization error in each of the rates, and the non-convex problem, which is inherently non-convex problem with respect to the precoders. Okay, so in order to first tackle those non-smooth function, I just simply replace the minimum operator with log sum exponents to approximate the minimum. Okay, so it's controlled by this alpha. So as alpha goes to 0, the approximation becomes tighter. So by replacing the x with the rates, we can simply have this log sum exponent of exponential function of the rate. And then the figures below shows how accurate the log sum exponential approximation. So with 0.1 alpha, we have almost like perfect approximation. But as the alpha increases, the gap between the approximation and the real actual maximization becomes like the gap is larger, becomes larger, but it's still like capture the trends of this maximum or the minimum function. And then we are going to use the generalized power iteration method, which is proposed in this reference. So in order to use this one, we have first normalized the precoder with the ADC, DAC gains. Okay, so this W is normalized. So this maximum transmit power can be trace of WW Hermitian is to be 1. Okay. And then we assume this maximum spectral efficiency, maximum transmit power to achieve the maximum spectral efficiency, which is natural. And then the next step is to handle the quantization noise terms. So we just reformulating this quantization noise covariance and ADC quantization covariance at the users in these following forms. Then putting all these together, we can formulate the common rate and the private rate in this following the variance of the Rayleigh quotient form. So each common rate and the private rate is log of some Rayleigh quotient function, and this W bar is the vectorized version of the normalized precoder. So it has like high dimensional vector. And A's and B's are defined as follows. And basically they are like a block diagram matrix. So it corresponds to each of the precoders. Each block corresponds to each of the precoder for each like common message and the private messages. So once it's done, we can use the log sum exponent, and finally the reformulated problem is given here. And then one observation from this formula is that since we know that this Rayleigh quotient problem has the optimal solution when the W is like the principal eigenvector of V inverse times A matrix. So motivated by this observation for this reformulated problem, I can say that maybe we can find the optimal solution by finding this first order optimality condition in the form of this generalized eigenvalue problem. So we first take the derivative of the Lagrangian problem of the reformulated problem, and then find the point where it becomes 0. And then we reformulate it to some generalized eigenvalue problem motivated by the Rayleigh quotient form. And then we can interpret, and then so the interpretation of this formula is that if we find some W here that satisfy this equation, it's one of the principal, one of the eigenvector of this matrix V inverse A. And then although I omitted in these slides, this lambda is proportional to the objective function. So if we find the principal eigenvector, it satisfies the stationarity condition, and also it finds one of the stationary points that maximizes the objective function. So based on that, we have to find the principal eigenvector of this generalized eigenvalue problem so that we can achieve the maximum stationary point. And then this principal eigenvector can be found by using some simple power iterations. Okay? So power iterations can be explained as follows, but let me just briefly explain how it works. So we project the Q, the random vector Q to the A, our like matrix. In our version, the matrix should be BKKT inverse times A KKT. So this we project the a Q to the A, and then we normalize it and we update the Q and we repeat until it converges. Then we can find this formulation, and once it's converged, it's guaranteed is to be the one of the eigenvectors or principal eigenvector. And then this is the algorithm diagram. So we have this iterative projection and normalization while it converges. So after the power iteration, we can find the principal eigenvector, which is the spurial local optimal solution. And then this simulations is evaluated for the ergodic sum spectral efficiency with respect to the SNR. So as you see here, I evaluate the proposed method and the proposed method without the rate splitting multiple axes. So I just use SDMA. And then I also evaluate the existing method and the linear precoders, conventional ones. And I see that as SNR increases, we fall into the interference limited regime, where the inter-user interference and the quantization error becomes larger. And in this system, we assume 4 base antennas and 4 users, and DACs we kept it with 3 bits, 3 bits, 3 bits, and 8 bits for each antennas. And once the observation is that compared to the SDMA, the RSMA gain is huge, and it becomes larger and larger as we goes into the interference limited regime. And let me show you why we have this such large RSMA gain for this particular system considerations. So this shows the antenna power ratio. So we have 3 antennas with 3 bits and 1 antenna with 8 bit. So this in low SNR, we have pretty well-distributed power across the antennas. But as the SNR increases, the most power are concentrated at the high DAC. That means if we increase the signal power, that increases the quantization error very significantly. So the algorithm does not want to use the antennas with low resolution DACs to avoid high quantization error. So in RSMA case, only like high DAC antennas are activated. But then if we assume like 4 users in this case, this only use like a single antenna almost. So it becomes overloaded system, but RSMA can handle this overloaded system by introducing the common message. So overall, it becomes like low private rate and high common rate. But the SDMA case, even with high SNR, the low resolution DAC antennas should be used, because if we don't use these antennas, we don't have like ability to separate the user streams because it's overloaded system. So RSMA provides better flexibility in optimizing the system with the heterogeneous low resolution ADCs. So it's like a flexible and suitable for this low power system, giving more flexibility in the optimization. Okay, so keeping this in mind, I'll extend my study to the rate and energy-oriented RSMA quantized precoding optimization by exploring the full design theory freedom. So let's say we see that the previous observation is like kind of antenna selection type of method, right? Because we have some antennas are almost deactivated, and we have some antennas are activated. So it's like antenna selection. So we want to introduce the antenna selection function explicitly so that we can optimize the system. So antenna selection basically reduces the RF chains with minimal impact. That's what we expect. And then it reduces the RF power consumption. So that means by turning off the antenna, we can save more power consumption of the base stations. Then maybe it gives you better like energy efficiency. Or the saved power can be used to increase the transmitted power if the total power is limited. Okay. And then our previous observation is here. So in the low SNR, if we have low DAC and high resolution DACs, the power is almost distributed like equally. because the quantization error from the low DAC is almost negligible compared to the noise power. However, when it comes to high SNR, low resolution DACs, it introduces very significant quantization error. As a result, it's almost turned off to avoid quantization error, and high resolution DACs are turned on. So in most cases, it gives you high interference, but the RSMA can handle this by introducing the better common rate. So this is very flexible solution, as I said. So my optimization considerations is categorized into like two different things, like performance metric and like what type of problem we solve. So let's first consider the spectral efficiency maximization subject to the transmit power constraint and the number of antenna constraint. In this case, this antenna selection does not give you the difference in this power constraint because this power constraint is only the transmit power considerations. So the benefit of turning off the antenna is not fully reflected in this problem. So it has some limitations in like full degree of freedom optimizations. But when it comes to energy efficiency, the base station power consumption is at the denominator. So the benefit of turning off the antenna in terms of power saving can be reflected. However, energy efficiency does not explicitly optimize the spectral efficiency. So after the optimization, although we achieve the best and highest energy efficiency, it may result in very low spectral efficiency. So we need something better. So what we have, so I first consider, so what type of degree of freedom in terms of like base station power consumption control or design can be considered. In terms of power consumption at the base station, maybe we can control the resolution of DACs, or we can control the number of antennas to be used, and also we can control the transmit power. So we have to have some control over all these functionality, and we have to carefully define the problem that reflects all these effects. And then my target should be maximizing the rate, which is the desirable directions of the future communications. And then in order to consider all these effects, the total base power consumption should be considered. So that by solving this problem, maybe we can optimize the quantization resolution, the number of antennas, and transmit power control. And then when it comes to transmit power antenna selection, we already observed that RSMA can provide more flexibility in these optimizations. So it can give you the better power trade-off. So I formulated this problem called like joint RSMA pre-coding, antenna selection, and the power control. So basically I consider the same system, the downlink multi-user MIMO system with the antenna selection functionality. And this is the sum rate optimization with the antenna selection and the pre-coders. But the constraint is now base station power budget. So under the total base station power budget, we have to find the best subset of antennas to reduce the power of the circuit. So this P circuit includes the effect of the antenna selection in terms of its power consumption. Okay? So this problem can be solved. If we solve this problem, maybe we can find the optimal number of antennas and optimal pre-coders and optimal transmit power. So which balances between the total under this total base station power budget. So it can give you like strategic balance of the transmit power and the antenna deployment. For example, if we use more antennas, maybe we can use less transmit power, or maintaining the same transmit power, we can reduce the resolution. So in this optimization, I just don't include the resolution optimization, but later I can show that by increasing the bits, like how well this rate can be given. Okay. So basically, I further assume the partial CSIT because as I mentioned, with low resolution ADC or DACs, the quantization error is inevitable. So the partial CSIT assumption is more like practical assumption. And then we assume that channel error covariance is given, but error is still a Gaussian type of noise. So we define the ergodic common rate and ergodic private rates and derive some lower bound. And then putting all these together, the sum rate can be given by also lower bound as follows. And if you note this equation, we have this conditional expectation given the estimated channel. So we're going to, but we have this estimated channel already. We're going to take the rate inside of this equation expectation as our objective function for a given snapshot of the estimated channel. So in this channel, in this function, then we first have to decompose power control and then the pre-coding. So we introduce this auxiliary variable, tau, which ranges from 0 to 1. So it determines the scale of the power compared to the total available power, transmit power. Okay, so we have to optimize this tau as well as the precoder F. And then we also define the normalized precoder W, which is a function of tau and F. And we also vectorize it as follows. And then we also use the GPI reformulation to represent this in this Rayleigh quotient form, assuming that transmit power equals 1. This normalized transmit power is equal to 1, meaning that we use the scaled power at maximum. Okay. So remaining challenges for this particular reformulation is that we still have a non-smooth function, which is minimum here for the RSMA. But we can also handle this with log sum exponential function. And this is non-convex function, but GPI can handle this non-convex function by finding the stationary condition with the eigenvalue problem. But then we still have the binary antenna selection function in the constraint. So this P circuit has this binary indicator. So we have to deal with this indicator further. So how I handle this indicator is as follows. So I first think about what's the equivalent condition of selecting the antenna. So if we select the antenna, that means the transmit power is non-zero. So in the same way, we think that if the precoder has non-zero power, then the antenna, the corresponding antenna is selected. So I replace the condition with the precoder condition. So two norm of the precoder should be larger than 0. Then we have active antenna. And then we replace with normalized precoder, and then we use some approximation for the indicator function. We can further reformulate the antenna power consumption as follows. And then to further apply the GPI, we reformulate all these into this simple equation. And then the antenna power can be summarized in this simple form. Okay. Then putting all this together, we have this reformulate problem. This is nothing but also the Rayleigh quotient functions, and this is also, it has some function of Rayleigh quotient. So by finding the optimally condition as well, by setting it to 0, we can develop the GPI pre-coding method for this reformulated problem. So we can optimize the W with the GPI method in the same way for given tau, and then we can optimize this tau with the just simple 1D gradient descent. And then alternating way, they are optimized. And at the end of the optimization, as we consider some, based on the antenna selection criteria, if some of the antenna has the power which is less than the criteria, we don't select. But if it's more than this criteria, we select the antenna. So all this functionality is included in this algorithm. And I can introduce the simulation result. So this is the ergodic spectral efficiency with respect to the maximum transmit power. And then we have 16 antennas and 4 users, and the total transmit power budget is 32 dBm at the base station. And we assume the homogeneous resolution DACs with 8 bits DAC bits. And we proposed this red curve and this this magenta curve is SDMA case. So this gap represents the RSMA gain. So RSMA can mitigate the interference as well as providing better flexibility in controlling the number of antennas to be used. So it has a huge gain over this SDMA case. For this previously developed GPI-based ray splitting pre-coding, this is in sine curve. So, but it does not really jointly optimize the transmit power or the antenna selection. So this gain represent the joint antenna selection and the power control gain. Okay? So that says, compared to the SDMA, RSMA gain is noticeable, and compared to the pre-coding optimization only case, this joint optimization like power consumption, power control, beamforming, and antenna selection is also very noticeable, even under the same RSMA framework. And we also evaluate the sum rate with respect to the channel quality. So as the channel quality decreases, we have decreasing the sum rate, but the RSMA gain becomes larger at some point. So this is some validation of how well the RSA can perform in the interference mitigations when we have inaccurate channel. And another observation is, what's the number of optimal DACs then for the homogeneous case? So I compared the result with the energy efficiency maximization work. So in this energy efficiency maximization work, the optimal energy efficiency is given when we use like 2 to 4 DAC resolutions, and the antennas selected is decreased as we use higher DAC resolution to provide better energy efficiency. But then this energy efficiency is maximized under this 2 to 4 DACs, but in our case, the rate is maximized with like 8 to 10 DAC bits. And then the number of selected antennas for each case, so homogeneous DACs with all 3 bits or 4 bits, or all 11 bits or 12 bits, we have lower lower antennas. So here, this range is the one that maximizes the ergodic spectral efficiency, and then the RSMA gain and joint optimization gain can give you can allow us to use more resolutions and higher number of bits, and which indeed can contribute to better channel estimation accuracies. So it's more beneficial to use higher resolution, and then this rate maximization with the power budget under the joint optimization can give you this result. So this is kind of different compared to the conventional belief that 3 to 5 resolution bit is optimal in terms of both the energy efficiency and also the data rate. But if we use full control over the transmit power, antenna selection, and the rate splitting, and etc., under the total power budget to reflect the benefit and the impact of those optimization, the optimal range is 8 to 10. So this is kind of different result. So in conclusion, we have identified a key trend like massive MIMO, massive bandwidth, and massive network. And the power consumption issue is one that we tackled, and we are introduced to use low power hardware. And RSMA is shown to work really well with the quantization error case and also the channel estimation error case. And then optimization to fully reflect the gain of over all these low power hardware and RSMAs. We have to consider the joint optimization between quantization resolution, antenna selection, and transmit power under the proper metric, such as rate maximization under the total base station power consumption. So we can fully explore the full design degree of freedom in terms of the power consumption. And then, briefly speaking, this I think summarizes all this talk. So we introduced quantization. to reduce the power consumption. Then we found out that the RSMA is good, really good to use when the power limit quantization case in terms of mitigating the channel estimation interference from the channel estimation inaccuracy, and also handling some like quantization related optimizations. And then RSMA indeed works really well with the antenna selection, providing the better flexibility in the optimization of the full system. And then further power control can be considered. And so we can use like full design degree of freedom in terms of the power consumption of the transmitter. So this joint optimization indeed allows us to use like higher level of quantization bits. And then we saw that the quantization bit can be as large as 10 bits. Okay, so this is kind of like optimal balance between the quantization, power control, antenna selection, and then RSMA can play a key role in fully utilizing this full degree of freedom when optimizing the future communication systems in terms of the power consumptions. Okay, so this will conclude my talk, and thank you for your attention, and any questions are welcome.
Yeah. So thank you for your very nice and very inspiring talk. So yeah, so please type any question if you have. So in the meantime, maybe I can start with some question. Okay. So right. So so I was wondering, so what's like a physical meaning of the ADC resolution bit optimization? So is that so we can really real time like on location for a different resolution bit for the different ADC with the AC?
Yes, it
Or
can be both. We can assume it can control the real time, but we can also assume that for a given consideration, like given number of base station antennas, given the transmit power budget or the base station antenna, a base station power budget, like how much or how many bits do we need? So after given fixing the bits, each of the antennas and the precoder and the transmit power can be optimized. And then this is the spectral efficiency achieved by each bit. So when it comes to this particular example, I would say that we can fix to use 10 bits for this case, and then we can perform the optimization, then it'll give you the optimal solution with respect to both the DACs and the rest of the criteria. So maybe in this case, we can just fix to 10 bits for this base station and then perform the optimization in this way. Then maybe you can expect the maximum spectral efficiency under the same power consumption at the base station.
so apart from the RSME, I mean, what is the motivation of a heterogeneous the DAC resolution heterogeneous resolution bit? I mean, when you talk about some benefit of RSMA, you take an example of like a 3 bit and an 8 bit like that.
Yes,
so is that practical kind of scenario which has a heterogeneous bit?
I don't really believe that's a practical scenario, but it's like based on our insight that if we have some heterogeneous bits at the antennas, maybe the antennas will have some random channel and also random quantization error. Then so those randomness can be more like flexible to assume to exploit when we have some heterogeneous bits. And then in our simulations, it also shows that we compare the heterogeneous case with the homogeneous case, but the optimal can be, it's not optimal, but higher improved SNR spectral efficiency can be achieved by the heterogeneous compared to all different types of homogeneous case. So maybe the insight is correct and better to use heterogeneous, but I don't think that's typical. But so I introduce rather to use antenna selection by fixing the bits same.
Yeah. So why I asked the question is, heterogeneous heterogeneous resolution bit are because of RSMA gain or just for the benefit for SDMA also. I mean, over the homogeneous cases.
Yeah, RSMA can work better with heterogeneous as we already observed, but it still give you better result in terms of the spectral efficiency, even with the homogeneous DAC bits compared to SDMA, because as you know, it's more like generalized solution compared to SDMA.
Okay, yeah, it quite makes sense. Yes.
Mhm.
All right. So, any
Any other
questions?
questions?
Yeah.
Yeah, there's one chat.
Yes.
Thank you very much for your presentation. In the figure on page 29, RSMA appears to outperform the SDMA. Could you please explain why the achievable rate of the RSMA saturated at the transmit power increases? Okay, so the reason is that we have the total power consumption fixed to 32 dBm. So this is like transmit power, but the total power consumption considers the circuit power as well. So if we increase the transmit power, maybe the total power consumption cannot be exceeded. So maybe at this point, it's better to use like around like 21 dBm, but meanwhile it's better to like decrease the number of antennas or selecting more antennas or selecting like selecting more antennas. So because of this total power budget, even with the maximum transmit power available at the transmitter, it cannot be increased to further. Okay. So I think this is the point where it gives you the best balance between the number of active antennas and the transmit power under this power budget. But when it comes to 10 dBm, this is too low transmit power, so it's better to increase transmit power instead of selecting more antennas. Does it answer your question? Okay, you're welcome. Wonjie, I think your sound is mute.
Oh, sorry. Yeah.
Okay,
Thank you.
another
Oh,
question.
I have another question.
Feasibility of the real-time pre-coder optimization to apply pre-coder optimization to real-world base station beyond deriving theoretical performance bound. It seems like we would need to consider dynamic scheduling and ensure optimization done with the channel coherence time. I'm wondering if this is realistic. Okay. You mean this means the proposed algorithm or like dynamic scheduling and optimization, both? Okay, so the current pre-coder, that's a good question, I guess. The current pre-coders is kind of like heavy to compute, although it's lighter than other like state-of-the-art pre-coders such as WMMSE, SAA here, or like SCA, SNS. Our proposed method is lighter, but still it's very heavy when it becomes very heavy when the number of antenna becomes larger, because as we observe here, so this is like very high dimensional vector when we have many number of antennas. So this optimization is related to projecting this high dimensional vector onto some matrix called I gave. So basically this projection and this inversion requires some significant load with the large number of antennas. So on the different direction of the optimization, our lab is trying to develop some low complexity pre-coding solutions, which does not scales with which only like linearly scales with the number of antennas, but rather it scales with the k cube, the number of users cube. So rather than the n, the number of antenna, it's the function, the complexity is order of k cube, the number of users. So in that case, with even with the significant number of like massive number of antennas, I would say that's going to be very fast, and hopefully it can work in the real time so that it can be optimized for each like channel coherence time. That's the best I can answer.
Okay, so
Is there any room for further reduce complexity in GPI? Yeah, there is. The conventionally it can be reduced to like n squared instead of n cube, and also k squared instead of k cube, by just simply changing some computation of this inversion, in a more efficient way, using some lemma. Well, so far I found that's the maximum we can do. Welcome.
Right. So, any other questions? So I think, yeah, RSMA turns out to be very robust to like a channel inaccuracy and then some overloaded system. But I think Professor Choi's work are also add some more like robustness toward like a DAC resolution bit, or I mean quantization bit. So I
And
think it's
also the antenna selection, yes.
antenna selections, yeah, could be very good. I think research directions. Yeah.
Okay.
Like, can you share like your future research direction regarding this field?
Okay, as I mentioned, we can try to more focus on reducing the complexity of this pre-coding, and also the scheduling. Basically, Juha Park mentioned all of my future research directions. So scheduling is one of the future directions. We have to schedule a better users that in terms of the RSMA, so we can increase the gain over the RSMA. And then we have to develop some lower complexity algorithm. So for the given set of users and given set of the antennas, maybe the complexity should be better. So those are the best way I can do. And the other directions, not in terms of RSMA, should be developing some like channel estimation techniques with the very low quantization bits. So it's been widely investigated, but maybe there's some more room to investigate.
Right. Thank you for your nice presentation and also Q&A session. So I think so it's I think we are almost closing time. So with this, let's conclude the talk. Thank you for your nice introduction again, nice your talk again, and with this, let's conclude the talk. Thank you. Thank you.
Thank you, everyone. Thank you.
Thank you, Professor Choi.
Mm.